Next, we look at the integral, the line integral over c of x squared dx plus y squared dy, where c is the arc of the circle x squared plus y squared equals 4, so radius 2 centered at the origin, from 2, 0, the positive x-axis, to 0, 2 on the positive y-axis, followed by the line segment. So we're going to have c be in two portions here. Let's have a visual of what this looks like. So we have here our circular arc, and remember, we're told from 2, 0 to 0, 2, and that gives us the orientation for what we're going to call C1. And then the segment goes from 0, 2 to 4, 3, and so that gives us, oh, I don't mean to put the arrow there. I'm going to put the arrow here, and I'll make it pink. That gives us our curve C2. The two of these together are the C over which we're integrating. Now, these two curves don't really have anything to do with each other. They have a common point, right? The end of C1 is the beginning of C2. That's kind of a requirement here. But we're going to consider C1 separately from C2. The parameterization of a circle is, well, a good parameterization is x equals 2 times the cosine of t, y equals 2 times the sine of t. That's a good general parameterization of a circle whose orientation is counterclockwise. Since we're only talking about the arc that exists in the first quadrant, t is going to go from 0 to pi over 2. Once we know what x and y are for C1, using differential notation, dx is negative 2 times the sine of t dt, and dy is 2 times the cosine of t dt. Let's now turn our attention to C2. C2 is a segment, and so we're going to use the same thing we used in the previous exercise here. Formally, we have r of t is equal to 1 minus t times the vector starting point 0, 2 plus t times the vector ending point 4, 3. Remember that that's describing the segment going from 0, 2 to 4, 3. Simplifying gives r of t is 4t comma t plus 2. Remember, this is a segment, so t is going to go from 0 to 1. In this case, x is equal to 4t, and so dx is 4 dt, y is equal to t plus 2, and so dy is equal to dt. The original expression, we were to compute the line integral over c of f of x squared dx plus y squared dy is then going to be equal to the line integral over c1 of x squared dx plus y squared dy plus the line integral over c2 of x squared dx plus y squared dy. What differs between these two expressions is not what we're looking at now, but what will happen when we substitute our parameterizations for c1 and c2. And here's what that looks like. Because for c1, x is equal to 2 times the cosine of t, and dx is negative 2 times the sine of t dt, in place of x squared and dx, we have 2 cosine t squared, the quantity of 2 cosine of t squared times negative 2 times the sine of t. And then for the dy, or y squared dy, remember y is 2 times the sine of t, dy was 2 times the cosine of t dt, and so y squared is 2 sine of t, the quantity squared, plus 2 cosine of t, and then the dt is factored out. In a similar way here, for C2, we're using the description of C2, x is equal to 4t, that's the parameterization, couldn't find the word there. Y is equal to t plus 2, so 4t squared, t plus 2, the quantity squared, and then for dx, we include the 4, and for dy, it's essentially 1. And again, both of those had the factor of dt. Now, again, just as with the segments, these integrals don't have anything to do with each other. And so we compute them separately. And I encourage you to stop the video now and do the work. Simplifying a little bit here, I've factored the 8 out of the first integral, and we're left with cosine squared of t times negative sine of t. That's going to be a u squared du. And plus sine squared of t times the cosine of t, again, a u squared du. And then simplifying the polynomials, we get 65t squared plus 4t plus 4 dt. First integral is again from 0 to pi over 2. Second integral still from 0 to 1. And then the arithmetic on this, well, after the calculus, turns out to be 8 thirds minus 8 thirds plus 65 thirds plus 2 plus 4, and simplifies to 83 over 3.